Yes, thank you very much for your kind introduction. My name is Umetsu. I come from Tokyo University in Sendai, Japan. I'm very happy to have an opportunity to talk my recent research work, and I really thank to the present session chair, professor, and organizing member of the conference for giving me a chance. I regret that I can't join the conference in person. I give you my presentation from my office. The title of my today's presentation is XMCD Study and the Pulsed Magnet Field, field for nickel, cobalt, manganese, indium, metamagnetic shaped memory alloy. I performed the direct observation of the soft X-ray absorption spectroscopy for the magnetic field in this multi transformation combined with a pulsed magnet. So I would like to show you the obtained experimental results. This is the outline of my today's talk. I will briefly give you the introduction of the nickel, cobalt, manganese, indium filament shaped memory alloy. I will also talk about the soft X-ray absorption spectroscopy, XRS, and magnetic cycle dichroism, MCD, and give you the experimental result and discussion, and finally summarize. They are collaborators, so Dr. Yasumura and Professor Nojiri, they developed, and also, Professor Narumi, they developed a pulsed magnet for X-ray absorption spectrometry experiments. So Dr. Kotani and Professor Nakamura, they are administrator of the 25 beam line in Spring 8, Japanese synchrotron radiation facilities. Professor Nakamura, he is now in Tohoku University. And Professor Kainuma, he discovered the present materials in 2006. Our collaboration has been continued to now. So this is the first report for the nickel, cobalt, manganese, indium, metamagnetic shaped memory alloy. The basic materials is off stoichiometric nickel to manganese, indium, Hoysura alloy. The cobalt is partially instituted in nickel to enhance the ferromagnetism and heighten the Curie temperature. As a result, the magnetic field can induce the inverse magnetic transformation from martensite phase to austenite phase. So we can observe MH curves, and also a large point resistance effect associated with the transformation is observed. The idea of the present research is to perform the X-ray absorption spectroscopy and the apply large field and investigate how to change the magnetic properties and structures in the magnetic field.
Excuse me, Professor Umetsu. There is some noise. Perhaps you're touching something while you are talking, so there is some ground noise.
Yeah.
Now it's perfect. Yeah.
Okay. Yeah. Okay. Now it's okay.
Yes. Now it's okay. Yes. Perfect.
Okay. Okay. So this time, I investigate the change of the magnetic properties and the electric structures when the magnetic field in this transformation occurs. Now it's okay?
Yes. Now it's perfect.
Okay. Thank you. So MCD is a variant of XAS in which circular polarized light is used. When electrons absorbed by an incoming photon, they are promoted from a core level up to the Fermi level. So we can obtain the information on the density of state in the conduction band. In the magnetic materials, the density of states for the two spin orientations, the absorption observed will then the different for the two light polarization. By subtracting the two spectra from one another, we obtain the difference in spin population. That is a MCD. The wavelength of the soft X-ray is 0.12 nanometer to 5 nanometer. So this range is right between the ultraviolet and the hard X-rays. So therefore, the soft X-ray energy is efficient to detect the electron structure of the 3D transition elements and rare earth elements. So this slide shows a list of the published papers for XAS and MCD for ferromanganese shape memory alloys. So because the nickel to mangan gallium is a typical typical material, so there are many, but not so many, that about 10 papers already published for the XAS MCD. But in the case of nickel to mangan indium or new ferromanganese shape memory alloy system, the only 3 papers are published, but all of the temperature dependence of the XAS. So, and there is no report on the direct observation for the transformation induced by magnetic field, because the large magnetic field is required for the experiments. For the systematic experiments, over 10 Tesla magnetic field will be needed. So superconducting magnet can apply such high magnetic field. However, large size of equipment makes it to be difficult to apply the soft X-ray XMCD experiments. The pulsed magnet allows us to obtain high magnetic field easily. However, the magnetic field is not static. Thus, high level of the experimental technique is required. So this table shows the example of the synchrotron radiation experiment equipment applying the pulsed magnet. So most of the experiments with pulsed magnet were applied for hard X-ray regions. Because hard X-ray experiment can be performed under air environment, for the experiments with soft X-ray energy region, so super high vacuum chamber is required. So this makes it to be difficult to do it. At the present, XMCD experiment with soft X-ray energy region combining pulsed magnet is only allowed at the spring 8 in Japanese synchrotron. So this is a published paper related to the experimental techniques. The chamber and the pulsed magnet, the space is filled by the liquid nitrogen, but now it is replaced by the cryostat. This is an order to this is in order to cool the pulsed magnet because the Joule heat is produced after applying magnetic field. So with using the 2 capacitor banks, the comparatively high long pulse is obtained, but only for the 60 milliseconds. The data were recorded by total electron yield method. We need to perform the experiments repeatedly if we increase the statistics of the data. So this is a photo of apparatus installed at the 25 beam line in pulse spring 8. So this is a sample preparing chamber with a load lock system. So this is a sample chamber, and they are on the 2-axis stage. This is a polycrystalline specimen, which is cut in the form and the slip shape and mounted on the sapphire stage. It was fractured in the high vacuum chamber to obtain the fresh surface like this. So this is a sample preparing chamber, so we can see the 2 sets of the specimen. And in the sample chamber, you see you can see the specimen before fracturing. So this is the experimental procedure for fabrication to the specimen. So this, So the specimen was fabricated by induction furnace melting, and the nominal composition is like this. And this is a condition of the annealing temperature. And magnetic measurement was performed by squid magnetometer and the extraction method with 18 Tesla superconducting magnet in high magnetic field center at my institute, IMR in Tohoku University. And the XSS MCD experiments performed at the beamline 25. So this data shows the magnetic data. So this is the temperature dependence of the magnetization and different magnetic field. The multi-stick transformation temperature decreases with applying a larger magnetic field like this. The large change of the magnetization, that is the metallic behavior, is observed associated with the reverse magnetic transformation in the MH curve. So this is a phase diagram using the magnetic this data. We decide the temperature at 150 Kelvin to observe the XAS signal with applied magnetic field. Magnetic moment, the magnetic moment confirmed at MH curve at 150 is about 6.3 MeV per formula unit. So this upper panel indicates the average XAS spectra for manganese. So here, as a spectra averaged between two kinds of circular polarization, so that is, the magnetic contribution is subtracted. So because I wanted to compare the intrinsic changes of the spectra in both phases, so XAS recorded at the magnetic field from 1 to 3 Tesla. So we gather the data during this magnetic field for the statics data. So this data 1 to 3 Tesla correspond to the martensite phase, and from 10 to 12 Tesla correspond with the austenite phase. For manganese, the spectra are completely overlayered as shown in the expanded scales, so no change of the spectra is observed between the two phases. So lower panel shows the XAS in the austenite phase obtained by right and left circular polarization light, and the bottom is a difference between them, that is the MCD signals. So we can see the large difference between them and the XAS and result in the large signals of MCD. So intensity of MCD roughly corresponds to the magnetic moment. So it is said that the magnetic moment is enhanced by the magnetic field induced transformation. So these are the similar figure for the nickel and cobalt atoms. In the case of these atoms, small but actual change of the average spectra are observed like this. The intensity of these atoms, so small but actual change. Yes, the intensity of the XAS in the austenite phase is slightly smaller than that in the martensite phase. So this means the decreasing of the number of the whole electrons. In other words, the increasing of the number of the electrons. So it is said that the density of states in the austenite phase is higher than that in the martensite phase, so suggesting that some change of the electric state. The sign of the MCD signals of the three atoms, this means the direction of the magnetic moments are the same. So the magnetic moments of manganese and nickel and cobalt are coupled ferromagnetically. In the XSMCD experiments, we can obtain the element-specific hysteresis by recording the MCD like this. We fix the photon energy. It shows the maximum intensity of the MCD signals. So such element-specific hysteresis is obtained, and the metamaterial behavior associated with the magnetic field-induced transformation is observed. Comparing to the MH curve measured at the same temperature, we can see width of the hysteresis is larger than that in the MH curves. The reason of the difference of the clarified, not yet, but we are thinking it will come from the surface effect of difference of the sample size. So it is well known that the XS experiments a surface sensitivity. So additionally, we used a small grain for magnetic measurement. It may correspond with a single crystalline grain, and we used the precrystalline sample for XS experiments. If the light beam concentrates to one grain, however, surrounding grain will affect the behavior of the martensite transformation. We analyze the XAS MCD signals by the sun bloom. This is a list of the spin magnetic moments and orbital magnetic moment and the spin magnetic moment and the ratio of the m orbital by m spin magnetic moment. So there is a trend that the ratio in the multi-site phase is larger than that in the austenite phase. The total magnetic moment given from the sum rule is about 6.1 MeV per formula unit, and this value is comparable to the value obtained by the MH curve in the magnitude data. So I'd like to discuss the change of the spectra by field-induced transformation. So as mentioned before, XAS in L3H in manganese has no change, but those for nickel and cobalt seem to change slightly. So they are expanding scale of the XAS in multi-site phase in the austenite phase. The lower panel indicates the subtracted XAS in each atom. So similar analyzing were reported by Crayer with the same system, but in the changing the temperature. The positive component observed at a certain photon energy and the behavior was compared with the theoretical calculations like this. And it was concluded that such a slight change of XAS for L3H for nickel atoms would be associated with the change of the density of state in the transformation. So it is difficult to discuss the detail in the present data, but we can say the nickel atoms correlate to the occurrence of the transformation than in the manganese. The excess for the cobalt atoms are, so the calculations for the cobalt atoms are absent, but the behavior seems to be similar to the nickel, so it will be correlate with the fact that the cobalt atoms are substituted in the nickel site. So, okay, I summarized my today's talk. So I measured the XSS MCD experiment and the pulse magnet performed for nickel, cobalt, manganese, indium ferrite shape memory alloy. The change of the MCD instances associated to the magnetic field induced transformation clearly observed with using a pulse magnet up to 12 Tesla. The total magnetic moment with using some rule is 6.0 MeV per formula unit and comparable to the magnetic data. The element specific hysteresis can be detected. Also, the hysteresis is somewhat larger than that of MH curve at the same temperature. And last, the change of the average to XAS spectra is observed associated with the transformation nickel and cobalt, suggesting the change of the electric state, but not in the change in the manganese. Okay, that's also my talk is finished, and thank you very much for your kind attention. Thank you.
Yes. Point is, as you know, in this metamagnetic shape memory alloys, I mean, the magnetic state in the magnetic phase is not fully clarified, I think. So, what from your results, what would you tell us? Which is the magnetic state in the magnetic phase?
In this present study, so we performed the magnetic field for the pulsed magnet, so it is very high sweeping. So this time we do not mention about the ground state of the multi-site phase with the magnetic properties, but without except for this present results, so our group's thinking that the ground state, property of the ground state of this materials is a paramagnetism or very complicated system, and so as you know, so but from this experiment, it is difficult to detail of the property of the ground state. Yeah.
Okay, thank you.